Dear students, you are welcome in this class, and in continuity to the last lecture, if you remember, I gave you one example. A field experiment was conducted and you have recorded some data. In this case, you need to compute different sum of squares. If you want to calculate the value of A and B, if you can find out value of A and B, that will give you a response equation, and this equation is the best fit. This is the best fit that will represent your data very well. So it has been done by some statistician, this equation y is equal to a plus bx. So you can see we need to fit this equation. First purpose is to make the equation, and in this case you have nitrogen levels as x and yield y as your dependent variable, yield as your y. So you have different parameters, and small x is equal to xi minus x bar. Likewise, you can calculate these parameters and they will help you to compute the value of B and A. And value of, first you calculate the value of B, summation xy upon summation x square, and then value of A simply by difference, y bar minus bx bar. With this relationship, you can work out the value of A. Now you put these values in the equation, and you must remember these formula, a value of B and value of A. You may get one small numerical on this in your exam. So we discussed this equation, and then we have gone for testing the linearity of this equation. Whether this equation is a linear equation, whether the data you have, observed data, actual data, is it following a linear relationship? Means there is constant return with the addition of each input level. So you want to prove it that it is genuinely a linear relationship. For this, you go for F test. And for F test, you need to calculate this value of F calculated, mean square due to regression divided by mean square due to error or residual. So you get F calculated, and it is more than your table value, 114. Therefore, this equation is significant. I explained you all this. Plotting the linear response curve, how to plot it. You can see it. Now you see from here we left. So characteristics of a graphical representation of the linear regression. What are the characteristics? You must remember these characteristics. These are sometimes come to your quiz exams. The line must be drawn within the range of values of x min and x max. It is not valid to extrapolate the line outside the range. So suppose your levels of fertilizer are, say, from 0 to 120. So you can have the line from 0 to 120. You cannot extrapolate it. You cannot make predictions for 130 kilograms of nitrogen, 140 kilograms of 140 kilograms, means you cannot extrapolate. Your results are valid only from 0 to 120 kg N per hectare. Within this range, you can make the predictions. So line must be drawn within the range of values of x min and x max. X min is 0, x max is 120. You cannot go beyond these values. Line must pass through the means of both the variables x and y. This line, if it is linear, if it is genuinely linear, then it must pass through the mean of both x and y. The slope of the line is b, also called as linear regression coefficient. It is the change in y associated with unit change in x. The line, if extended, must intersect the y-axis at the y value of a. Means at zero level, what is the value of y? That is represented by a or intercept. The simple linear correlation analysis deals with the estimation and test of significance of linear correlation coefficient, which is a measure of the degree of linear association between the two variables x and y. Let us see what are the important features of the correlation coefficient, that is small r. So sometimes this correlation coefficient is written as small r, sometimes it is written as capital R. Similarly, coefficient of determination, it is usually written as small r square and also as capital R square. So it does not make a difference whether you represent it by small r or capital R, you can use both. But normally statistician, what the statistician like, that if your relationship is simple linear correlation, or if the association is simple correlation and regression, then you use a small r. And if it is multiple relationship, then you use capital R. And you know, simple correlation and regression means only two variables are involved. Multiple means more than two, that is three or more variables are involved, then we call it multiple correlation and regression analysis. So if you have multiple correlation regression analysis and using coefficient of determination, then use capital R square. Otherwise, if you use small r square, that is also okay. You are not doing any mistake. So features of correlation coefficient. The value of correlation coefficient lies in the range of -1 to +1. It can be minus 0.98, minus 0.6, minus 0.120, etc. Or it can be 0 also. And then up to +1 means plus 0.678, plus 0.999, etc. So range between -1 to +1. And extreme values indicate the perfect linear association. Higher the value towards left side or towards right side means more the values means you have perfect linear association, more strength of association. But if it is 0, means there is no relationship between two variables. And the minus and plus sign, it just indicates the change, whether it is negative correlation or positive correlation. This minus has nothing to do with the absolute values of the correlation coefficient. If absolute value of correlation coefficient is minus 0.998, that does not mean that it is in minus, this value is in minus. Minus is just indicating the change, that one is increasing, other is decreasing. Otherwise, minus is not associated with the value. Now, suppose you know the correlation coefficient, then how it will help you in the interpretation. So what you can do, you can square it. If you square this value, it becomes your coefficient of determination. And do not worry, very shortly you will learn what is coefficient of determination. So in this case, suppose your correlation coefficient is 9.9, R value. Your implication is you square it. 9 square means 0.81. And 0.81 can be multiplied by 100. That means it becomes 81%. So what is relevance of this? You can see that the 81% of the variation in variable y can be explained by the linear function of the variable x. Means 81% of the data is following linear association. Simply, to be more simple, 81% of the data is following linear function, but other data we don't know what kind of relationship it is having. The minus or plus sign attached to the R value indicates the direction of change in one variable relative to the change in another variable. Means this negative sign is when your relationship between two variables is negative or correlation is negative. Even though 0 R values indicates the absence of linear relationship, but it does not mean that two variables are not having other kind of relationship. They can have curvilinear kind of relationship or some other kind of relationship. So it is possible for two variables to have a non-linear or curvilinear. Means first we test whether it is linear or not. If it is linear, fine. If it is not linear, then we will look for other kind of relationship, that is non-linear or curvilinear relationship. Some more features of correlation coefficient. The value of R does not change if all values of either variable are converted to a different scale. The value will not change. Value of correlation coefficient will not change because it is unitless. There are no units of correlation coefficient. And if you convert kg per hectare into tons per hectare, the correlation coefficient is not going to change. The value of R is not affected by the choice of X or Y. If you exchange them, if you convert dependent variable, if you consider dependent variable as independent variable or vice versa, it will not change. The correlation coefficient values will not change. It measures the strength of a linear association. It is not designed to measure the strength of an association that is not linear. It measures only when the relationship is linear. Now, what are the requirements for testing the significance of R? By now, you understand how to compute the correlation coefficient. You must be knowing in ISRA also, they must have taught you what is the formula of correlation coefficient. Now, you want to see whether correlation coefficient is significant or not. The values are genuinely statistically differing or not. For this, you have certain tests to test the significance of R. So before that, following requirements should be met when testing hypothesis or making other inferences about R. Correlation coefficient means it needs to follow certain statistical principles. First thing, the sample of paired data is a random sample of quantitative data. When you have recorded X1, Y1, or Y1, Y data, dependent variable data, they must be randomly sampled. They must be randomly sampled, and this X is already fixed. So random sampling is important. The sample data have not been collected using some inappropriate methods. Means all statistical procedures should be followed. Your sample should be a random sample. Visual examination of the scatter plot must confirm that the points approximate a straight line. So I have shown you sometimes back a positive correlation, negative correlation. Just by seeing the scatter plot, you will get idea whether the data is following certain trend or not. So it must follow a linear trend or linear pattern. Then only you can go for analysis of coefficient of correlation. Any outlier must be removed if they are known to be errors. So sometimes you can have any outlier. Outlier is a data which is not normal, which is not following the trends followed by other data. Means suppose the height of the students in this class is say 6 feet or say 5.5 to 6 feet. Okay, we can record the data because height varies from 5.5 to 6 feet. But there is a person who is having height of 8 feet, which is unusual. So that will be considered as outlier, and we will not take that data. So that is your outlier, which is in general beyond the imagination and which is not following in some general range. So now you know formula how to calculate the correlation coefficient. So simplest thing is that R is equal to summation xy. This is, you remember, we have taken the deviations against mean of x and y and then multiplied that. So it gives you summation xy divided by underscore summation x square into summation y square. You know how this summation x square has come and y square has come. You already know it. And you get 0.991 as your correlation coefficient. So up to now, what you could see is the fitting the equation means you have to find out value of A and B. Then we have tested whether it is significant or not. In the last case, you have seen it was significant. Plotting the equation means transferring your equation into a graphical form, and then coefficient of correlation, how it is calculated. And then comes the coefficient of determination that will come little later. And there is one more step, that is fifth step. I will tell you later. But before I proceed, your doubts and clarification you can seek. Yeah, Wahid, any problem? Wahid,
Yes, sir. Yes, sir.
you have any problem?
No, sir. It is very clear.
Yeah, good. Actually, over years, I had interaction with Afghan people, and many students have been here in IRI outside. I observed that mathematics of Afghani people is excellent. Your mathematics is very good. Am I right?
Yes, sir.
Why it is so?
Mathematics, sir. The statistic, especially the statistic one, is better from Indian students, sir. Because we are studying basic mathematics here, and the statistic based is just in the university. After 12th class, we have the general mathematics, Sarji. In general, we are good, and the statistic is new to us, Sarji, in the ARI. And usually, I'm using Excel sheet, Sarji, for these formulas, and sometime paper base as well. I have developed these formulas, Sarji, in Excel sheet, Sarji.
Good. Thank you. Thank you, Bhai. Thank you. So now question comes. Now you have seen formula of correlation coefficient. Question comes whether it is significant or not, because value varies from -1 or to +1. So whether it is significant or not. So test of significance of correlation is very, very important. And there are two methods to test the significance of correlation coefficient. First method is using t-test. This correlation coefficient can be tested by a t-test, whether it is significant or not. Other option, method 2, is the test statistics is R, critical value of RR from table. So method 2, if you remember, R.A. Fisher is considered as father of agricultural statistics, or maybe experimental designs, I think. He is father of experimental design. What do you think? R.A. Fisher is father of agricultural statistics or father of experimental design? Anybody?
Sir, experimental design, sir.
Huh?
Sir, experimental design.
Yeah, I think so. You are right. So he is considered as father of experimental design, R.A. Fisher, and he has helped us a lot. I would say he helped us. Otherwise, he has also created so much of statistics for us. So in this case, you can see that he has developed some relationship with t-test and correlation coefficient, and he has made a table. Which table is like your F table, T table, Z table, like that. And in that table, based upon degrees of freedom, n-2, he has given the table value of correlation coefficient. And you need not to do anything. If you calculated a correlation coefficient value, suppose it is 0.923, and then you go to the table, you straightway go to the table, and there are 2 or 3 levels of significance. Select the level of significance of your choice, and then look for the table value of R on n-2 degrees of freedom. And then compare to the table value. If your calculated value is more than the table value, that means correlation coefficient is significant. Otherwise, it is not. So method 2 is the easiest one. And if you want to do method 1, you can do it, but answer will remain same. So suppose you adopt method 1. So you need to calculate T value. T is equal to R upon underscore 1 minus R square and N divided by N minus 2. So here you will calculate the T value and then you see the table value. Table value at N minus 2 degrees of freedom, table value of T. And if it is more than table value of T, then it is significant. So this is how you can use two methods to see the significance of the correlation coefficient. Now method 1 is explained here. So we calculate the T statistics. T is equal to R into underscore N minus 2. So either you use this, T is equal to this formula, or you use this formula. Meaning is same. Some mathematics has been done, but you will get the same value of T. Whether you use this formula or you use this formula, you will get the same value of T. So then the calculated value of T is, if it is more than table value at prescribed level of significance, then your correlation coefficient is significant. The significance of R, the distribution of the correlation coefficient R for samples from a bivariate normal population having correlation coefficient rho is equal to 0 has been discovered by Fisher, who linked it with the student's t-test based upon some transformations. So this is how Fisher has come to our help. And then you can see what Fisher has done. The table you are seeing before you, this is known as the correlation coefficient table, and values of the correlation coefficient for different level of significance. Suppose my N minus 2 was 5. So I will see against the 5, and I can see if the level of significance is 0.1, the value is 0.6694. If the level of significance is 0.05, values of table value is 0.75 R5. So if this is the condition and my correlation coefficient values are more than 0.7545, then it is significant. Otherwise, it is non-significant. So this is how you can directly get your answer from the R tables. Test the significance of the R by comparing the computed R value to the tabular R value at N minus 2 degrees of freedom. The R is significant at the prescribed level of significance if the computed R is greater than the tabular R value. Any problem in this? Now, test the significance. Suppose your correlation coefficient was 0.991 and table value of R at 2 degrees of freedom was 0.950. So you can see at 2 degrees of freedom under 0.05. 0.05 means 5% level of significance. So value is 0.950. And then at 1%, it is 0.991. At 1%, if you see at 2 degrees of freedom, you see at 0.01. 0.01 means 1%. So value is 0.990. So you can see that it is significant at 5%, but it is not significant at 1%. So here the R values are significant at 5% level of significance and non-significant at 1% level of significance. In the above case, the 100 R square, as I told you, you square the value of this R and then multiply it by 100. So you get 98.2%. Means 98.2% of the variability in the dependent variable can be explained by the linear function of the variable x. This is the meaning of this. You square the value, find out the coefficient of determination, multiply it by 100, you get 98.2%. Means most of no other. So I can say this is the best fit. The fit was the best. The equation was significant. Therefore, most of the variability has been explained by linear function of x. Now, you can write it in several ways. The inferences, like last case, you have written the inference like this. Same way, you can write more inferences, like I read for you. We conclude that 100 R square, that is, if you do the calculation, 98.2% of the variation in the seed yield of mustard. So, which is your dependent variable, seed yield of mustard, can be explained by the linear association between the seed yield of mustard and the nitrogen application rates. This implies, another version is, this implies that about 1.2% of the total variation in seed yield of mustard can be explained by factors other than nitrogen application rate. Means nitrogen accounted only for the 98.2% variability. Other variability could be due to some other factors or other reasons, or 1.8% of the total variation in seed yield of mustard remained unexplained. So let us try to understand the coefficient of determination. Whenever you face interview, many times people ask you, tell me difference in correlation coefficient and coefficient of determination. So students normally answer that correlation coefficient, first you define the correlation coefficient and then simply say that if you square the value of correlation coefficient, then it becomes coefficient of determination. That is true. But exactly if somebody asks me that how to explain how it is used, what is the meaning of coefficient of determination, then you can see it now. So it is the sum of squares due to regression when expressed as a proportion of the total sum of squares. So in example 1, I have shown you the sum of square due to regression, if you remember how to calculate the sum of square due to regression and total sum of square. And you have also seen the residual sum of square, So what is the proportion of regression sum of square in relation to total sum of square? Means what proportion has been accounted by regression sum of square out of total sum of square. Less the error, least the error, higher the value of R square. That means R square will tell you the fitness of the data. Suppose R square is your 0.98, then that means 98% is from variability is from regression. Variability accounted by regression. Only 2% could not be accounted. If your R square is your 0.74 and it is 74%. So 74% means remaining is your 26%. So 26% is the error. So that means the line that you have fitted is not the best fit. So therefore, higher the value of R square, better is the fit. So for example, if you get R square value 1, then there will not be any error. The total sum of square is equal to regression sum of square. Means all kind of relationship is there. This line is representing the best, the data the best, and all the points, observed point are on the line when R square is 1. So it measures the amount of variation in Y accounted by the variation in X. This is 1. R square indicates the proportion of the variation in the dependent variable explained by the model. For the present example, the R square is equal to some, this is the formula of R square. You can directly calculate by squaring the correlation coefficient, and you can indirectly calculate like this. The value will remain same. There will not be any change. So R square is equal to sum of square due to regression. You have seen in the ANOVA divided by total sum of square, which is your summation y square. So if you put the value in the last example, you get 0.982. The value of R square is the proportion of the variation in y that is explained by the linear association between x and y. Now, characteristics of R square. The value of R square quantifies the goodness of fit. How fit is your equation? A fraction between 0 to 1. The value of R square is always from 0 to 1. It is never from -1 to +1. Remember, value of R is from -1 to +1. Value of R square is from 0 to 1, +1. Higher values indicate that curve comes closer. Higher value indicate that curve comes closer to the data, more close to the data. Statisticians use uppercase for the result of non-linear and multiple regressions, and lowercase for the simple linear correlation and regression. When R square is 0, the best fit curve fits the data no better than a horizontal line. When R square is 1, this is important. R square is 1, all points lie exactly on the curve with no scatter, means they are exactly lying on. So that is the most best fit. When we can think of R square as the fraction of the total variance of y that is explained by the model. So there are different ways to explain the coefficient of determination. Only R square, not the main criterion for whether a fit is reasonable. A higher R square tells us that the curve came very close to the points, but does not tell that the fit is sensible in other ways. So many times, you know about a statistician, they never satisfied and they go on. I will show you where these statisticians love to play with the data. Now, up to now, you have seen that there were several steps like fitting the equations, testing the significance, linearity, then plotting the equation. Then we have seen correlation analysis, correlation coefficient, and coefficient of determination. And one more step is there, which is known as residual analysis. So what is there? You have two kinds of data. One is your observed data, which is recorded from the field and which was significant. Other is your predicted data. Predicted data, if you see any line, this is the line. So you can see here R square is equal to 1, means all the data points are touched by the line. So if you want to make some predictions here, not here, let me check you one more. Actually, I do not have a figure. I will explain you later. So you have observed data, actual data, and you can also have corresponding predicted data. Corresponding predicted data for 0 observed data and for 0 predicted data. In the equation, if you put the value of x, you can predict the y. So for respective x, you can get predicted data or estimated data. And then you take the difference of both observed data and predicted data. That difference is known as residual analysis. And line also, you have seen what is residual. So residual are the distances which are away from the line. So you take those differences, those are actually residual. And statisticians are happy to go for residual analysis. Whatever is left, they have further statistics of, there are many books on this subject, residual analysis. We need not to go into much details of residual analysis, but statistics is there for residual analysis also. I will just show you the residuals and so on. Now we go to another kind of relationship, non-linear or curvilinear relationship. So sometimes you get linear relationship significant and sometimes it may not be significant. If it is non-significant, that does not mean that there is no relationship between two variables. It can have some other kind of relationship. The relation between variables, when the regression equation is non-linear, quadratic, cubic, or higher order, is called the curvilinear or polynomial relationship, where you can have x square, x cube, and so on. So it is a form of linear regression in which the relationship between independent variable x and the dependent variable y is modeled as the nth order polynomial. So we'll see it curvilinear, like plant growth. You see, I have explained you sigmoid curve. That is not a straight line. The curvilinear relationship among variables is quite common in biological organism. The response to a variable is rapid at the beginning. You have seen in sigmoid curve, slower at the intermediate level, and could even become negative at high level of the variable. So sometimes it may follow exactly your law of diminishing return kind of pattern, which is your non-linear or curvilinear. Non-linear, curvilinear. The pattern of plant growth over time shows you curvilinear kind of relationship. Curvilinear relationship is a polynomial type of relationship except the linear relationship. Y is equal to a plus bx. The regression models or equations follow here. Quadratic. भाई पानी मंगाया था, गिलास दिया था. Quadratic, you can see y is equal to a plus bx plus cx square, cubic, and so on. Already discussed this. Now, you have seen that we have followed certain steps in linear regression analysis. Similarly, here also, you need to follow certain steps. First is fit the quadratic equation. So here you need to find out the value of a, b, c. Quadratic equation is a kind of non-linear or curvilinear relationship. So even in non-linear, you can see linearity is hidden. Curvilinear means part of the line or equation is linear there. So here you need to fit the quadratic equation, means you need to work out the value of a, b, and c. Here you got two regression coefficient. One is b, other is c. Test the significance whether the equation is linear or not, and then whether it is curvilinear or quadratic or not. Test is available. Plotting the quadratic response curve, how to plot it, computation of R and R square, and you can also test the significance of correlation coefficient and inferences about R square and computation of optimum economic dose. So these are the important steps. If you can miss, you can see the sequence of the things, so it becomes easier to understand. Now, first job is fitting a quadratic response equation. Here now you understand fitting means to find out the value of A, B, C, and if you put those values in the equation, that is the best fit line. The response to fertilizer, plant population, irrigation, and other inputs generally follows quadratic relationship. Somebody must have taught you relationship between plant population and growth of the crop, or biomass accumulation, leaf area index, and so on. So those are actually quadratic kind of responses. So in case of fertilizer, most of the time it is quadratic response, particularly in case of NPK. Before fitting such response equation, your data has to be significantly different. Yeah, as I told you in the beginning, F test has to be significant, and then the fitting of quadratic equation is shown below with a hypothetical example. This is somewhat hypothetical example, not exactly hypothetical. I have taken this example from Gomez and Gomez book. So you must read one chapter from Gomez and Gomez book on correlation regression analysis, that is linear relationship and non-linear relationship. There are two chapters you can read. So in this case, fit a quadratic equation from the data given in the table and calculate the optimum economic dose of the K2O potassium when the cost of 1 kg K2O is ₹10 and price of 1 quintal of rice is 500. 1 quintal means 100 kg. 100 kg price is ₹500. So the prices are very low. Just to for ease in calculation, I kept it 10 and 500. Otherwise, price of rice is not 500 now. It is very high now, more than 1600 rupees a quintal. And similarly, price of potassium is also very high. But this is just representation of calculation. Now you see, this is very important, how to fit a quadratic response equation. How to fit a quadratic response equation means you need to find out value of A, B, C. So this is manually, when you do by your calculator or by calculations, computer can do it in 5 seconds, but you will do it in 1 hour. So what are different steps to find out value of A, B, C? Now you are fitting the equation. So first is to calculate the corrected sum of square. Certain corrected sum of squares are to be calculated, like in case of linear relationship. So sum of square are summation Z1 square, Z2 square, Y square, Z1 capital Y, Z2 capital Y. So many parameters you need to calculate. Number 2, for our example, the linearized form of the second degree polynomial is y is equal to a plus b z1. Remember, it is capital Z1 plus c z2. Here comes the statistician. The statistician wanted to measure the linear distance. So if you have a curve, if it is not a straight line, if you have a curve, then it is not possible to measure the distance from the data up to the curve, because it is curve. It is not a straight line. From a straight line, you can easily measure the distance, but from curvilinear curve, you cannot measure it. So what statisticians have done, they have linearized the equation. Equation is y is equal to a plus bx plus cx square. So in place of x, you can see y is equal to a plus b z1. So they have put z1 by some transformations. Certain transformation were done by statistician, and they have, after transformation, they have made a new variable which is capital Z1, and it is equivalent to your x, which is your independent level, independent variable, or rate of potassium application kg per hectare. Then comes plus CZ2. So this is x square. So square has been linearized by some relationship, and it has been converted into Z2, capital Z2. And Z2 is equal to x square. So this is how this statistician have done. I know only this part, that x is equal to Z1, and then x square is equal to Z2. You can consider it like this, and by having this assumption, you can calculate rest sum of square. Corrected sum of squares can be calculated. Beyond this, I do not know. I do not have knowledge how and why it was done. I do not have much idea, but I can say in this, if you want to calculate value of ABC, you need to convert this x into Z1. You need to consider x is equal to capital Z1 and y is equal to capital, x square is equal to capital Z2. Now you see how to calculate or how to compute different sum of squares. So column 1 is your Z1, capital Z1, 0, 30, 60, 90, 120. So then mean of x or mean of Z1 is 60. Then column number 2 is your grain yield, that is capital Y kg per hectare. Values are there and you can calculate the mean of Y. Mean of Y by making the total of 5 values and divide by 5. You get mean. Then comes your Z2. Z2 is your x square. So now you need to square the value of Z1. Z1 is equal to x. So x square means you square these values and make the column number 3. So 0 square 0, 30 square 900, 60 square 3600 and so on. Now you come to column number 4, small z1. Small z1, it can be calculated by z1 minus z1 bar. So z1 is your first column and subtract the mean, that is z1, capital Z1. So you get small z1, column number 4. Column number 5 is simply squaring it. When you square the column number 4, you get column number 5. Then column number 6 is Z2. Z2 is related to dependent variable, that is your yield. No, sorry, Z2 relates to your x square. Now, small z2, you need to calculate this parameter, which is equal to capital Z2 minus Z2 bar. So you need to calculate it from column number 3. If you subtract the mean of x square, mean of Z2, from this you get this Z2 minus Z2 bar. Then column number 7, you square the column number 6. And then column number 8, y minus y bar. You subtract the mean from the column number 2. You get these values in plus and minus. And then square. This is total sum of square. This is total sum of square, column number 9. Square the column number 8. Then column number 10 is small z1y. You know where are these columns, you get it. Then similarly column number 11 and 12. And on the bottom you make the total of all. So you can make the total of all. Some are 0. Some are 0. When you take the deviations against mean, their sums are always 0. So any problem in this? This is calculation. You have to do it if you want to find out value of A, B, C. Of course, there are some other methods also. Uncle R.A. Fisher has done a lot of help, and Yates, they have made some calculations very, very easy. It is difficult. Method of least square gives you some difficulties, but there are certain methods people used to do manually. And Fisher and Yates method of fitting this quadratic equation is very, very easy. But now there is no fun because people are not using it. Now people use mostly Excel or softwares to calculate this, but we should know some fundamentals or some background of the theories. So anything from this table, if it is not understood to you. Now you can calculate the value of B, C, and A. So value of B, you can calculate by this formula. You do not worry, you need not to remember this formula, but quite complicated. And all these parameters you have estimated in the last table. If you see the sum, the summation, you see these all are available with you. Corrected sum of square, means, etc. So you put all these parameters here, the values, and you get 26.646. Similarly, value of C can be calculated by this formula, and you get it in minus. Minus means some decline is happening. Your marginal return or has become minus, or your coefficient has become in minus. This is a regression coefficient C, which is in minus. Now, value of A can be calculated by difference y bar minus B Z1 bar minus C Z2 bar. So you put these values, you get value of A also, 4861. So now you get value of ABC. You can put these values in the equation. So finally, your equation is this. You can see this is before you. Now you want to calculate R square, capital R square, coefficient of determination. It can be directly calculated. You can calculate correlation coefficient, or you can calculate R square and take the under root of it. That will be your correlation coefficient. So R square is equal to this formula. Put the value from the table, you get 0.996. Now F, now you want to test whether it is a quadratic equation or not. For this, you have F test. So this is the formula of F test for quadratic equation, n minus k minus 1, and all these parameters. Here k means number of variables linearized. So here you have linearized two variables. One was x, other was x square. So therefore, in place of k, you will put 2, and n means number of pair of observation. So in this, you have 5 pairs. 1, 2, 3, 4, 5. So 5 pairs are there. Therefore, you put value 5 in place of n. And then you get F calculated as 245.32. This is your F calculated. And you compare with the table value, which is 99. Even at 1%, it is 99. So computed F value at F1, F2 means in both the cases, degree of freedom is 2. 2 for F1, 2 for F2. The estimated quadratic regression equation is significant at 1%. If it is significant at 1%, that means it is surely significant at 5%. So the inference is that yield response to rise to K2 of fertilization can be adequately explained by the quadratic equation. So here you will not get your linear equation significant. You can try yourself to fit the same data as a linear data. You will find that linear relationship would be non-significant in this case. And 99.6%. R square is 0.996. That means 99.6%, which is very high. Of the total variation in mean yield was explained by the quadratic regression equation estimated. Means out of 100 total sum of square, 99.6% is attributed to regression, or in this case. Now, the determination of optimum economic dose is very, very important. Now you need to apply some economic principles to this, and rate which produces maximum economic yield. So we need to find optimum dose mainly to get maximum return, and other is to prevent pollution of the environment. Because if you use excess dose of fertilizer, that can pollute your environment, and also it will increase the cost of cultivation, and sometimes excess dose can reduce the yield also. Therefore, optimum dose is very, very important. If I ask you what is meant by optimum dose, you can reply, sir, it is the rate which produces maximum economic return. In case of linear response, you cannot determine the optimum dose. A rule of thumb is that optimal rates determined on an economic basis are smaller than those required to produce maximum yield. So definitely economic rates are lower than the rates which are required to produce maximum yield. Maximum yield will never give you maximum return. It is the optimum yield that will give you optimum returns. So you want to find out the optimum dose of the fertilizer. People have done large experiment on this across the world, and they have found that on an average, 80% of the maximum yield dose, 80% of the maximum yield dose is your optimum economic dose. Normally, if you do not want to do calculation and so on, and if you have experience and you found that highest dose where you get maximum yield is so much, so just multiply that by 80%, and you will get the optimum dose, or 0.8 can be multiplied. So economic yields target usually do not exceed 80% of the maximum potential yield. It does not include economic cost. It is considering only other costs are considered as common. So from the quadratic equation y is equal to a plus bx plus cx square, optimum economic dose can be worked out. This is the formula to calculate the optimum economic dose, q upon p minus b whole divided by 2c. You must remember this formula. So b and c are regression coefficient. You can directly take them from the equation, and q is the cost of 1 unit of input. That is your fertilizer in this case. What is the cost of the 1 kg K2O? And P is the price of 1 unit of output. What is the price of 1 kg of rice? So here commodity is rice, fertilizer is potassium. Now see how to work it out from the table. Maximum yield dose is minus B divided by 2C. This is the formula used to calculate the maximum yield dose. Put the value of B and C from the equation. In the equation, you have these values. You can take A value is here, B value is here, and C value is here. Remember, C is in minus here. So optimum economic dose Q upon P minus B upon 2C. Here you can put the values of Q and P. Cost of 1 kg K2 is rupees 10. Price of 1 kg of rice is 5, 10 by 5, minus this is B minus B, and divide by 2 into C. C is minus 0.1178. So you get 104.6. This is your optimum dose. This is your optimum dose. Now, there are several parameters related to fertilizer use. Response at optimum dose. If you want to calculate the response at optimum dose, yield at optimum dose minus yield at control. This is the formula. All these formulas you need to remember. Put the value of X 104.6 and 0 in the response equation. Response equation in place of X, you can put the optimum dose first time, and then second time you put 0. So you get two answers. One is 6359.96 and 4861.66. So response is the difference between these two. You get 1498.3 kg per hectare. Means this much of increase or this much of response was only because of fertilizer, potassium fertilizer. This one, because you have taken optimum dose, you have predicted the yield at optimum dose, and then this yield is 6359, and yield at control, predicted yield at control. The difference is this. This is the actual response. If I ask you what is response of fertilizer, means yield at a particular dose of the fertilizer minus yield at control. That is the response. That is the additional yield, extra yield you got due to application of fertilizer. Now, response in kg per kg K2O. So you can take the response at optimum dose divided by optimum dose, you get 14.32. Then comes the profit. Profit, value of the produce minus cost of K2O per hectare. Value of the produce means what is the price, economic produce you have, minus cost of K2O. So first you calculate value of produce means response at optimum dose. How much extra yield you got? 1498 into selling price. What is the selling price? Rupees 500 or 5 rupees 5 a kg. Cost of K2O, cost of 1 kg K2O into optimum dose. So you can work it out, cost of K2O per hectare, and then profit is equal to 1498.3. This is the extra rice you got into 5 is the 1 kg rice price, minus 10 into 104.6. 10 rupees a kg is the rate of K2O. This is your cost, and you get 6445.5. This is your profit per hectare, 6,445 rupees per hectare. Return in rupees per rupee on K2O is spent. So profit per hectare divided by cost of K2O, you get 6.16. If you spend rupees 1 on K2O, you get 6.16 rupees. Of course, it is hypothetical example. Finally, uses of response curves are interpolation, interpretation, Relative response can be known. Interpolation, you can interpolate. Interpretation, you have seen a lot of interpretation have been done. Economic response, to find out optimum dose, to increase the efficiency. So a lot of functions are there for response curves. Now your questions are welcome. You have some 2, 3, 4 minutes time. Anything you want to discuss, you are welcome to discuss.